6.6 is all about conditional probability of independent events. Earlier, in our independent events set of notes, we learned that the probability of the intersection of A and B was equal to the probability of A times the probability of B. We're going to add two more independent event equations. The probability of A given B will be equal to the probability of A. The same way, the probability of B given A will be equal to the probability of B. This makes sense if you think about what an independent set of events is. An independent set of events are two events where one does not impact the probability of the second occurring. So, if you want to find the probability of A, given that B has occurred and they're independent, it makes sense that the probability of A will remain the same and unaffected by the fact that B has occurred, because that is the definition of independence. So, let's take a look at some examples using these two new formulas. Also, when we do these problems, keep in mind that we still have this first equation as well. Determine if the following are independent or not. Part A. What is the probability given that a red marble? What is the probability of picking a red marble on the second pick, given that the first marble was red and What is the probability of picking a red marble on the second pick, given that on the first pick a red marble was selected and not replaced? As we had mentioned before, anytime you do not replace something, that would change the probabilities and therefore would make them not independent. Part B. What is the probability of getting a head on a coin, given that a head was previously flipped on the same coin? A coin does not care what has been flipped previously, so these two events would be independent. C. What is the probability of rolling a 4 on a 6-sided die, given that a 3 was just rolled on the same die? Again, a die does not consider what was rolled prior, and therefore the probability of rolling a 4 would not be affected by the fact that a 3 was just rolled, and therefore would be independent. Now let's go ahead and start using our equations to calculate some probabilities. In example A, we have the probability of A given B is 0.274, and we want to know the probability of A. Something very important I forgot to mention. In the directions, we're told that these events are independent. That is extremely important because we need to know that the events are independent in order to use the equations up above. If they were not independent, we wouldn't be able to use the equations up above. Now, since we know they're independent, we know that the probability of A given B is equal to the probability of A. Therefore, the probability of A should be equal to the same value, 0.274. In part B, we want the probability of A and B, we have the probability of A and B, and we also have the probability of B. We want the conditional probability of A given B. So let's start at what we want, the probability of A given B. What we know from the equations above is that the probability of A given B will be equivalent to the probability of A. We don't have either of those, so this doesn't seem to help us very much. So let's take a look at what we do have, the probability of A and B and B. We have an equation that relates A and B, and that would be the equation we learned back in our independent notes. Probability of A and B is equal to the probability of A times the probability of B. Let's fill in what we know. A and B is 0.168, and probability of A is still unknown. Probability of B is 0.42, so we can find the probability of A. We'll find the probability of A by dividing by the 0.42, which is multiplied by it. Taking 0.168 divided by 0.42 will allow us to find the probability of A. In this case, it's going to be 0.4. Once again, I've had this calculation at a time. This gives us the probability of A, but we want the probability of A and B, A given B. As I had mentioned in the very first line, though, these two are the same, which means that the probability of A given B should also be 0.4. In part C, we have the probability of A given B, and we have the probability of B given A. If we have the probability of A given B, remember, if they're independent, the probability of A should be the same. And the probability of B given A is also the same as the probability of B. So we also know the probability of A and B. We want the probability of the intersection, probability of A intersect B, or A and B. In our first equation, we see that that probability will be equal to the probability of A times the probability of B, which we now know. So let's plug in each of them. 0.4 for the probability of A times 0.5 for the probability of B. This should allow us to calculate the probability of A and B. Multiplying 0.4 and 0.5, we get the final probability of A and B as 0.2. So notice each example will be different, but you have to use the three given independent formulas to manipulate them and solve for the one piece you're looking for. This leads us for the test of independence. These equations will always be true for independent events, and if they're true, the two events will be independent. So if we're trying to see if two events are independent, we can try any of them to see if they're correct, and therefore the two events would be independent. So once again, these three equations are only for independent events. However, we cannot use them until we know that they are independent. We can use them to check for independence, but we can't use them until they're independent. However, in the set of notes, I wanted to throw out the reminder that we can calculate the conditional probability of any two events, whether they're independent or not, using the following formulas. The probability of A given B is equal to the probability of A and B over the probability of B, and the probability of B given A is equal to the probability of A given B, A and B all over the probability of A. If you remember, I thought of this as the probability of two events as the and over the second letter. This is for any two events, regardless of whether they're independent or not. Let's take a look at the following examples. In number 3, we want to determine the missing probabilities if the two events are independent or not. Notice we do not know if the two events are independent or not. This means that we cannot use the circled equations listed above for independent events. However, we can check them to see if they're independent. So, let's take a look at what we do know in part A. We know the and probability is 0.048. I'm going to go ahead and list that in the Venn diagram, although the Venn diagram may or may not necessarily be needed in each of these problems. The and is the middle, so I'm going to go ahead and fill out that number in the middle. The probability of A is 0.12. That's the entire circle right here. I don't want to fill that out on the left because that includes the 0.048. If I subtract these two, 0.12 take away 0.048, I'll get what's left over in the bubble on the left, giving us 0.072. I also have B, 0.5. And again, if I subtract the two, 0.5 minus 0.048, I can get what's in B, but not the and, 0.452. Once again, this may or may not be necessary. We want to calculate the probability of B given A. Because we don't know if these are independent or not, I can't just simply assume that it's going to be 0.5. So I'm going to use the old school conditional probability calculation of the and, probability of A and B, divided by the second term, in this case, A. I plug in the and probability, which I was given, 0.048. Divide by the probability of A, which is also given, 0.12. If I use my calculator to calculate these, 0.048 divided by 0.12, I'll get my conditional probability and get 0.4. Notice that the conditional probability of B is not the same as the regular probability of B. So since the probability of B given A is not equal to the probability of B, the two events cannot be independent because this is one of our independent statements, that the conditional probability and the regular probability must match. So no, they are not independent. The Venn diagram, notice, was not really needed in this particular example because I was given all of the information that I needed to calculate my conditional probability. In example B, we have the and probability again, probability of A, and the probability of A given B given to us. And we want to know the probability of B. Before I talk about the probability of B, take a look at what we have. We have the probability of A and we have the probability of A given B, both as 0.5. I feel like that's important to us. This is actually one of the statements for an independent event listed above. If the probability of A is equal to the probability of A given B, that means that the two events are independent. And now that they're independent, I can use any of the independent equations to solve for the probability of B. So I can take the probability of A and B and set it equal to the probability of A times the probability of B to solve for B. Notice, I can only use this equation now that I know that they're independent. So the probability of A and B is 0.2, probability of A is 0.5, and the probability of B is unknown. To solve for the probability of B, I need to get rid of the 0.5 by dividing by it. 0.2 divided by 0.5 gives me 0.4 as the probability of B. Notice this time I didn't use the Venn diagram because I didn't need it. Let's take a look at C. We have the probability of A and B, the probability of A, and the probability of A or B. We want to know the probability of B, and we want to know the probability of A given B. All right, so, again, all of these problems are different. So you just have to use the equations that you can to find what you're missing. So we want the probability of B. The only calculation that we have right now that involves B alone will be our independent equations, or it's actually embedded in the conditional probability of A given B. So if I try to set up the probability of A given B, I notice that it's the probability of A and B, which I have, so that's good. But it's over the probability of B, which I don't have. So there's two things in this equation that I don't have, which is not going to help me right now. So how else could I solve? Well, this is where I might turn to a Venn diagram and just fill in what I know. Right now I know that the probability of A and B is 0.2, so I can fill out the middle. The probability of A is 0.35. The probability of A, though, is the whole circle. So you don't want to put 0.35 just on the left piece, because 0.35 also includes that 0.2. This means that the probability, what's left over in A will be 0.35 take away the 0.2, or in other words, 0.15. Now I know the probability of A or B. That's not going to be what's left, that's going to be the whole thing. Since the probability of A or B contains both of these bubbles, and the 0.15 and the 0.2, in order to solve for what's left, I have to take the whole probability of the OR and take away not only the 0.15, but also the 0.2 shared in the middle. When you subtract the two pieces you know, you get what's left over. So in this case, that would be 0.4. So now we know each of the individual pieces. So how will this help us find the probability of B, or the conditional probability? Well, now that we have all the individual pieces, we can find the probability of B by adding up the two pieces that make up B. So 0.2 and 0.4 make up B. That means that the probability of B has to be 0.6. And now that I know B, I know two of the pieces in our conditional formula, and I can solve for the probability of A given B. Plug in your and, 0.2, divide it by the B, which we just calculated, 0.6. If we finish this, this becomes 1/3, or 0.33 repeating. If we take a look at our probability of A given B and our probability of A, we notice that these are two different probabilities, and therefore, since they don't match, they cannot be independent. Let's take a look at our last example in this set. Here we have the probability of A and B, the probability of B, and the probability of A. And we want to know the probability of B given A. So we can go ahead and start putting things in our Venn diagram. Well, actually, no, wait, let's not. Let's go to the calculation of our conditional probability. The probability of B given A. For any two events, independent or not, this probability will be equal to the and over the second letter. So it will be equal to the probability of A and B over the second letter, in this case, A. We know both of these pieces, so we can calculate this conditional probability. A and B is 0.14, and A is given to us as 0.7. When we divide these, we get 0.2. So this is our conditional probability of B given A. Looking at our conditional probability of B given A and the probability of B, we see that they match. When the conditional matches the original probability, this means that the two events are independent. And we can circle, yes, they are independent. Now please keep in mind, this wasn't the only way to tackle this problem. I could have checked for independence by using the probability of A and B, B and A, to see if when multiplied, they equal the probability of A and B, in which I would have found that they were independent, they were the same. And then I could have just used the fact that they were the same to find the probability of B given A. So there are also multiple ways of going about these problems. Let's take a look at a more involved problem. Here we want to determine the probability and once again see if they are independent or not. But we have a more concrete scenario. We have a 20-sided die and two specific events. Event A is a value greater than 15, and event B is a factor of 20. Before I begin, I want to calculate the probabilities of A and B separately. So let's list out the events in each, the outcomes in each event. For A, values greater than 15 would include 16, 17, 18, 19, and 20. And we don't go further since this is only a 20-sided die. With these 5 outcomes out of 20, that would give us a probability of 5 out of 20, or reduced to 1/4. For the probability of the factors of 20, let's first list the outcomes for the factors of 20. 1, 2, 20 isn't divisible by 3, but it is divisible by 4, and 5, not 6, or 7, or 8, or 9. 10 works, 11 doesn't, 12, 13, 14, 15, 16, 17, 18, 19, but 20 works. So here we have 6 factors of 20. So the probability of just B is 6 out of 20, or 3/10. So these are our probabilities of A and B. The next question wants the set of A intersect B. Notice this is not a probability. These are the actual outcomes within the intersection. If I look at my 2 sets and I just look for any overlap, I see the only number that is in common is the 20. This means that there's only one outcome in my intersection set, 20. And therefore, the probability of the intersection would be that one outcome out of the 20 possible outcomes. Let's calculate the conditional probability of B given A. Please note, we don't know if these are independent right now. So before we can calculate the probability with our independent equations, we have to go back to the old school version of calculating a conditional probability. So I'm going to go ahead and do it down below where there's a little bit more space. The probability of B given A will be equal to the probability of A and B divided by the probability of the second event, or in this case, just A. We conveniently calculate the probability of A and B up above as 1/20. And the probability of A was also calculated up above as 5 out of 20. Once again, notice I'm using the unreduced form because in our conditional probabilities, those 20s will cancel, leaving us with 1/5. Now, if you look at that 1/5 probability and you compare it to the probability of B, note that the probability of B given A is not equal to the probability of B. So what does this tell us? Well, if the conditional probability does not match the original probability, this means that the 2 events are not independent. Next, we'll calculate the probability of A given B. The probability of A given B, we have to calculate with our old school fashion and over the second letter because they're not independent. If they were independent, we could simply just take the calculation for the probability of A. So we do the and probability on top and the second letter, in this case B, on the bottom. A and B, once again, we already know as 1 out of 20 from our previous calculations. The probability of B is also calculated above, and again, I'm going to use the unreduced form, 6 out of 20. 20s cancel, leaving us with 1/6 as our probability of A given B. And there's our answers. Notice that I didn't fill out the Venn diagram. Often you will be given Venn diagrams, but you don't necessarily need to fill them out. If you feel like you would like to fill them out, you may, but you don't have to unless stated to. One last thing in this set of notes, and that's conditional probability and mutually exclusive. Now, let's talk about what mutually exclusive means again. Mutually exclusive events are 2 events which have no overlap. This is not to be confused with independent events, which are 2 events which don't affect the probability of the other. Since mutually exclusive have no overlap, when you're talking about the conditional probability of one event given that the other event has occurred, the probability must be 0. Because if one event has occurred and the other event can't happen at the same time, that means that the first event couldn't happen, and therefore would be impossible, 0. So if you just take a look at our visual example, white marbles and red marbles are clearly mutually exclusive because this marble cannot be white and red at the same time. If we have the probability that it is red, if we're given the fact that it is a red marble, it makes sense to say that the probability that it's a white marble would be 0 because no white marble will also be red.